vector. So again applying, we have three cases. Firstly, we have to find the electric field on the surface. On the surface, the distance d is equal to r. The r is the radius of hollow sphere. So we apply the Gauss's law. Phi is equal to integral of E dot ds vector is equal to the charge q upon epsilon naught. The charge q is on the surface distributed uniformly. So E into ds cos 0 degree, E vector is parallel to ds vector. So we have theta 0 degree. This is equal to E into total surface area. Here we have to take the surface area of this sphere, hollow sphere, which is equal to, surface area is 4 pi r square. R is the radius of the sphere. So this is A into 4 pi r square. So from these two expressions we have, this is equal to q upon epsilon naught. So E is equal to q upon 4 pi epsilon naught into r square. So this is the value of electric field on the surface of hollow sphere. Now we will find electric field outside the hollow sphere. Again we draw the diagram. This is hollow sphere which is having positive charge distributed over the whole surface. Surface area is 4 pi r square. So radius is r. Let us take the point P outside the sphere, and it is at a distance d is equal to r dash from the center O. Now we will draw an imaginary Gaussian surface which is including this point P. And we will take small segment ds. Its surface area vector is ds vector, and the electric field is also along this direction E vector. So again applying the Gauss's law, we have E into ds into cos 0 degree integral is equal to q from epsilon naught E into ds is the equal to q upon epsilon naught. Now when we are taking ds integral, we are talking about the Gaussian surface, which is dotted surface. So its a surface area S dash, this is equal to 4 pi into r dash square. Since its radius is r dash, so we have area S dash is equal to 4 pi r dash square. So we have E is equal to Q upon 4 pi epsilon naught into r dash square. This is the value of electric field outside the hollow sphere. Now the third case is electric field outside the hollow sphere, inside, sorry. Again we draw the diagram. The positive charge distributed uniformly, the radius is r. Let us take the point P inside the sphere. It is at a distance d is equal to r from the center, and we have total charge q which is distributed over the surface. Now inside the hollow sphere the charge will be 0. So when we talk about the point P, at this point also q is 0. Now since E is equal to q upon 4 pi epsilon naught into distance square, since d is q is equal to 0, so E is also 0. So the electric field inside the hollow sphere is 0. If we draw a diagram, graph between the electric field E and the distance d, so this will be like this. D is equal to r. Up to distance r, the electric field will be 0. At the surface, when the distance becomes equal to radius of the sphere, the electric field is maximum. Then when we go outside the hollow sphere, the value of electric field will decrease. So this is the graphical representation of electric field for the hollow sphere. Now next we come to the electric field due to a solid charged sphere. The expression for the solid sphere will be same. Suppose we have this solid sphere, and we have given a charge q, positive charge q to this solid sphere. It is uniformly distributed on the surface and inside the hollow solid sphere. The radius of this charged sphere is r. So when we talk about outside electric So, putting the values of V dash and V, we have V dash is equal to 4 upon 3 pi r dash cube divided by 4 pi epsilon naught into r square into 4 upon 3 pi r cube. So, when we solve this, we have rho r dash upon 3 epsilon naught. So, this is the value of electric field for the solid sphere inside. Now, we will talk about the electric field due to a charged straight conductor. For a charged straight conductor, let's suppose we have this conductor, it is given a positive charge Q over the whole length L. In this case, we have sigma, this lambda is equal to Q upon L. This is a linear charge density. From Gauss's law, phi is equal to E into S integral is equal to Q upon epsilon naught. In this case, suppose we have to find the electric field at this point P. So, we will draw a Gaussian surface cylinder including this point P. At this point P, the value of direction is perpendicular. At this surface also the electric field is along this direction. Here also electric field is along this direction. Here the ds vector is perpendicular. Here also ds vector is perpendicular, but along perpendicular direction ds vector is parallel to E vector. So, we can write the flux through these two surfaces will be 0, but along the perpendicular direction it will be maximum. So, we can write this solving integral. We have E into total surface area is equal to Q upon epsilon naught. The surface area for this cylinder is equal to 2 pi r L. L is the length of the conductor and r is the radius of cross section. So, we have E into 2 pi r L. The value of Q is lambda into L. So, when we solve it, we have E is equal to L is cancelled out. So, we have lambda upon 2 pi epsilon naught into R. This is the electric field for the straight conductor. So, next is electric field due to a charge sheet. If we talk about a charged sheet, it is given positive charge Q uniformly distributed over the whole surface S. Here we have this surface charge distribution sigma. This is surface charge density, it is equal to Q upon S total surface area. Now, by applying the Gauss's law, here we have two types of, if we have to find the electric field at this point, this will be along this direction E vector, surface area is also along this direction ds vector, and so the electric field will come out is equal to sigma upon epsilon naught by applying the Gauss's law. This is for the thick sheet. If we talk about thin sheet, this will be equal to sigma upon 2 epsilon naught. So, these are the Gauss's law and its applications. So, that is all for now.